Hello everyone. This is a talk about simpler index types. I am Tesla. The idea of index types was presented initially as silly type families, where the motivation is related to type-safe ASTs and their interpreters, where we specify the return type of data constructors so the type checker could filter out the impossible constructors doing pattern matching. We refer to the parameters that can be specialized by constructors as indices. It then became a well-known GHC Haskell extension called GADTs, and the standard data type constructions in dependently typed programming languages such as Agda, Lean, or Idris. There is one thing special about index types in a dependent type system, that indices are not only types but also terms. Here are some classical examples in the Agda programming language: the finite set type fin and the sized vector type vect. They allow inductive definitions of not only types but also functions that return types, aka type families. The parameters of the families are called indices. The indices specify how the constructor selection process works in the pattern matching of indexed types. When we perform a pattern matching against a fully applied index type, we unify the index arguments in the type and the constructors. This unification process has three potential results: success positively, where we allow and require a pattern matching clause for this constructor; success negatively, where we do not need to provide a pattern matching clause for this constructor; or a failure, where the type checker cannot make a decision and disallow pattern matching for this type. In this example, test prime, we are performing a pattern matching on the type fin1, and the f0 constructor succeeds positively, so we are required to perform a pattern matching for it, while the argument of the f-sub constructor succeeds negatively, so we do not provide a pattern matching for it. The syntax of indexed types is too flexible. In the previous examples, we have only put fully applied types or data constructors in indices. Apart from these, we can also write more complicated terms such as lambdas, functions, pi types, etc. But the pattern matching of these types becomes much less useful. Only when the types are applied by a free variable can they be pattern matched against. For example, simply trying to pattern match on the type of the listed constructors will lead to a unification failure. The current syntax of general index types is too flexible that undecidable unification problems might get generated from them. So the following question naturally arises: can we have a more restrictive syntax that rules out these complicated problems? And the answer is yes. First, we stop specifying the return type of data constructors. By doing so, we obtain a syntax that is very similar to the Haskell standard data types. Then, we allow pattern matching to be performed on the type parameters of an inductive type. The constructors remain the same. This example pretty much explains everything you need to know about simpler indexed types, but here are some technical details. The patterns in front of the data constructors specify the availability of constructors. Pattern matching has three potential results, just like term unification, but it's much simpler both to implement and to use. These patterns are unlike patterns in normal functions. We allow duplicated and incomplete pattern matching clauses, just like in this fin example. The syntax reads, if the index is sucks something, then both constructors are available. If the index is 0, then no constructor is available, so this type becomes the empty type. Otherwise, we disallow pattern matching for this type. Now, let us do a comparison with some related work. First of all, comparison with general index types. In general index types, we have term-term unification, and in simpler index types, we have term-pattern unification. The latter is already a part of the evaluator, so we can reuse some code in the implementation. Also, it is very difficult to implement the term unification algorithm that does not assume the k-axiom of the identity type. There are a lot of publications by Jesper Cox that deals with these problems in Agda. An identity type that does not assume k is essential for homotopy type theory and its variations, such as cubical type theory or the hot eye type theory. So, if we want to do hot with general index types, we will have to implement the term unification algorithm without k. Apart from implementation simplicity, we also get some performance boosts. In general index types, we specify the indices in the data constructor's type signatures. So there might be some fields stored in the constructors that are only used in the indices, like the variable of name n in both constructors of fin on the left-hand side. In the case of simpler index types, these fields just do not exist, so we get the index erasure optimization for free. Second, comparison with an encoding based on large elimination and records. We can also encode some indexed families by large elimination and records, like in this vector example. However, simpler index types enjoy several advantages. First of all, they have named constructors, so they generate more user-friendly error messages. Second, in simpler index types, we do not have to respect the rules for pattern matching in function. A large elimination is a function, so it has to be covering, non-overlapping, and structural recursive. This is quite inconvenient to work with. Just try to imagine the definition of the finite set type based on large elimination. There is one more problem of the function encoding, that non-indexed recursive types cannot be encoded this way, such as the natural number type. We do not have such problems because we do not check the termination of the types. In the end, we talk about some downsides of simpler index types. Simpler index types cannot express a bunch of definitions due to the restriction of pattern matching syntax. For instance, if we translate the standard Martin-Löf type theory identity type into our simpler syntax, we get a nonlinear pattern matching, which is illegal. We believe that adding a built-in identity type with some syntactic sugars will work around this problem. In case the identity type is independent of unification-based pattern matching, we can get a type theory with the same expressivity as vanilla Agda type theory without implementing the notoriously complicated term unification problem. Cubical type theories and other hot variations are such type theories. There are other index types, but we conjecture that all general index types can be encoded as a simpler index type and the built-in identity type. Here is an example taken from Jasper Cox's paper and its encoded version. Note that the equal sign is the name of the identity type. In the paper, we have formalized the type checking algorithm of simpler index types in the setting of a simple dependently typed lambda calculus with function definition and pattern matching. We have also discussed a sound and complete translation from simpler index types into general index types. In the end, we would like to talk about the implementations and the applications of simpler index types. The proposed syntax has been implemented in two dependently typed programming languages: Arend, developed by JetBrains Research, and Aya, developed by a yet unnamed team and some open source contributors, both based on a variation of homotopy type theory. So we have the homotopy type theoretical path type playing the role of a built-in identity type. The so-called path type is a type that satisfies the introduction rule and the elimination rule of the standard Martin-Log type theoretical identity type. The implementation of path type in both of these programming languages are independent of the term unification algorithm. This means that both of these proof assistants are sufficiently expressive as vanilla Agda if our conjecture holds. We have not yet discovered any counterexample. However, in a recent version of Arend, the developers have implemented a simplified version of dependent pattern matching as a convenient syntax for writing proofs. Thank you for your interest in our work. We appreciate your questions.